Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about water cooling. So let's dive right into it. Now, before we understand the cooling aspect of it, we must understand the water itself. Water, it's one of those things that is safe, meaning it's safe for us and also safe for the environment, meaning it's not one of those things that is like, if it spills in the environment, it's dangerous for us or for the environment. It's one of those things that can be classified as inert. It's reactive, but inert in terms of toxicity. And it's also very easily available and cheap compared to everything else that we try to use for cooling purposes. And it has very high heat capacity as a general everyday, liquid. Now, there is only one liquid that I can even find that even comes close to the capacity of water, that is ammonia. And be mindful, ammonia only works at certain temperature ranges. So if you are in that temperature range, ammonia could be a better replacement, but most of the time water is the king. And its raw heat capacity is ludicrously high, meaning it takes a lot of heat before it rising its temperature. What does that mean? That simply means, think of this like you can have a water tank, right? It could be, let's say, as small as 25 liters. Generally that's the water heater size that we have, a water geyser, and you turn on the power heater. Again, that heater is consuming 1 kilowatt of energy. Here's the, if you have a thermometer in that water, nothing will be happening for a few minutes. Like literally few minutes you can be consuming electrical units, but nothing is happening. It will take its sweet time to raise its temperature, and it will keep taking that. It won't be like, okay, 0 to 1 degree takes a lot of time and then it's like very easy. 1 to 2, that much energy. 2 to 3, even more energy. 3 to 4, like it takes same amount of energy. It's very vast amount of energy it consumes. So it takes a lot of energy. That's the capacity aspect of it. It's very grand, and it also has very large range for us, 0 degrees Celsius to 100 degrees Celsius. Now 100 degrees Celsius, that simply means almost even in a desert it will simply not boil. Like if you have it in a bigger, it will slowly evaporate, but it will not just like boil. 0 degree, unfortunately for us, 0 degree is not cold enough, simply because if you live in upper latitudes, northern latitude or southern latitudes, you could reach a point where 0 degrees too goddamn hot, because temperature can drop into minus 20 degrees Celsius. So in those scenarios, that's not cold enough. So that's water. Now there are two methods of operation, meaning there are two things you can do with water. First thing, you let it evaporate, meaning you have something hot, you dump water into it and it boils. That's it. Now that's what we call evaporative cooling. You let the water take the heat and boil off, meaning you do not like try to keep it flow around it, try to keep it, cool it down, nothing. You just like let it go. And it's an open loop system. Benefit, it takes insane amount of heat to take liquid water, transition it into steam. It takes a lot of energy. That's awesome. But side effect, it's an open loop, meaning you are consuming water. So whenever you see thermal power plants, generally that's their weak link. Many power plants around the world has to be shut down simply because they drained their water supply, meaning they had a small lake, they drained it dry. They had a river, they drained it dry. That sort of things have happened. Many power plants had to be shut down because of the water shortages they cause. So open loop, while it does work, while it is cost effective, it is very destructive in terms of like, do not try to do this unless you have like continuous flow of water. And then you have water cooling, where you're using water as a thermal conductor. Basically, you have a stuff that gets hot and you want to take that heat away to somewhere where you can easily dispose of it. That's way you are utilizing, you're not using phase change, you are using water as a thermal conductor for moving heat from high flux, meaning, for example, your car engine, combustion engine generally have ludicrously hot temperature around the cylinder walls. Those puppy can get hot, and that hot is like so tightly packed, almost nothing will do. Even evaporative cooling will barely able to cool it down. So you have to almost submerge it. At that point in time, you are running water around it, and then water is going into big radiator in front of your car and then slowly dumping that heat away effectively. So you can take very high concentration of heat and dump it into larger surface area where you can take it away. Almost like how your computer liquid cooler works. Like CPU, very concentrated heat, radiator, large cool surface area. Water is not changing phase. All you are doing with water is just conducting it from point A to point B. It's like, take it heat from here, dump it there, take it heat from here, dump it there. You're not letting it change phase. So these are two modes of operation. Now water may have 0 degrees Celsius and 100 degrees Celsius. Like 0 is for freezing, 100 is for boiling, but that is assuming one core aspect, standard atmospheric pressure, meaning around 14.7 psi or almost 15 psi. Now why does that matter? Well, here's the pressure is a very important factor, meaning if you control the pressure, how much pressure water is in, you can control the boiling point, meaning you can control the you can raise it or lower it. Now why would you want to raise it? For example, let's say you are running a coal power plant. Now 100 degrees Celsius, it's hot, but not that hot. It's not able to take almost oomph the coal is producing. What if you raise the pressure from 1 bar, basically 1 atmosphere almost, to let's say 10? Now your boiling temperature is 180 degrees Celsius, meaning water will take a lot of energy to boil. Now you can go even higher than that to, like, let's say 15, and 15 you can almost achieve 200 degrees Celsius. Be mindful, it goes even further than that. And basically nuclear power plants, the water is put under serious pressure to achieve seriously high temperature, meaning it will not boil. And it also happens in nature. For example, below the seabed, you can have underwater volcanoes. The water will not boil simply because the water pressure is too goddamn high. So that's the whole point. The pressure allows you to control vector, meaning you're like, are you happy with 100 degrees Celsius? Use it normally. Not happy with 100 degrees Celsius? How about you raise the pressure? That's one vector. How about other direction? For example, you want to boil water off to cooling purposes, basically exactly how your refrigerator works. But if you know anything about refrigerator, basically fluids and basically gases that we use in them, they boil at very low temperatures, meaning around minus 16 degrees Celsius to minus 50 degrees Celsius. So they take a lot of heat away and drop the temperature. Now if you cannot go that low, you want to be at least lower than human body temperature for active cooling. So you want to be around minus 10 degrees Celsius, or even not minus 10 degrees Celsius. 10 degrees Celsius is cold for us. Now if you drop the temperature, basically pressure, to 0 psi, you can easily boil water off at 10 degrees Celsius and even lower. Basically it also drops very dramatically. You can easily drop from 100 degrees Celsius to 50 to 30 to 10 degrees Celsius. In some scenarios minus, but generally no system is that vacuum tight. So is there a use of this phenomenon? Absolutely. A majority of absorption chiller utilize this factor, that water boils at lower temperature if you have partial vacuum there. So they use salt to absorb basically water moisture, create a partial vacuum there, and water boils at low temperature. Benefit, you can cool the fluid. Now you can achieve cooling power of almost minus 5 degrees Celsius, some company claims, but it's rarely achieved. But you can easily achieve like 4 degrees Celsius. Now 4 degrees Celsius of water, it's a lot of cooling. So in terms of cooling convection, meaning it can take heat away from anything hot. So that's awesome. You can heat it up, you can cool it down, and you can also add additives to it. That's another aspect of it, meaning for some scenarios, let's say in India, we don't think too much about it, because again, if we leave our car outdoors, nothing's gonna happen to it. Now if we do the same thing in Canada, you could have a scenario where you put the car outside and it self-destructed in the morning. It's like, what the hell happened? Temperature drop, meaning water inside the radiator could freeze, become into ice crystal, destroy the pipe from the inside. So in those sort of scenarios, you have to add some additives, some type of salts that will allow the freezing point to drop below 0, meaning you can drop it to, let's say, minus 14 degrees Celsius. So if the outside temperature only drops to minus 10, you will not have a freezing hazard in your car. So that's why we can control the multiple aspects of water quite precisely. Especially majority of the control lies in the pressure, and then you can add additives based on what you want. Now, what about the tools of it? That's medium. We are talking about the water as a medium. What about the tools? Now, tools wise, it's surprisingly easy to make heat exchanger for water. That's one good thing about water. So you can ask any Tom, Dick and Harry, they know how to. If they can work with metal, they can build you a good heat exchanger. That's awesome. Now, different metal can be utilized. You can use steel. It will not last long, but generally if you add good paint to it, you can use it for a very long time. And if you use stainless steel, even longer than that. Aluminum, longer, but it does have some drawbacks. Mainly being the price. You can use copper. Generally high flux scenarios are using copper. For example, stators of power plant generators, they generally use water. Now you're like, wait a minute, isn't water conductive? Well, technically no, water is not conductive, simply because if you have distilled water, it's surprisingly good insulator. You need to add impurities into that, which generally majority of the water that we see around us have impurities. For that reason, we treat water as a conductor, as a safety precaution, because you cannot take the risk like, hey, it may be distilled water. Generally it's not. So that's why power plant cooling relies on water to be distilled as in clean AF, no particulates, nothing, no salts, nothing. It has to be distilled AF. If it's not, shock. So that's the one thing. If you have impurities, it will cause corrosion also. It will only cause electrocution, it will also cause corrosion. Corrosion is very destructive, specifically for lower grade materials. It will simply destroy it. It's like, this is the one destructive aspect of metal, water and metal combination. It will just eat through it. It does not matter how big it is. It can eat through giant warship. That kind of corrosive power is there. And another issue is, because water is conductive, you also have to take into consideration of galvanic corrosion, meaning this was lesson learned by many people long ago, and then PC community recently, simply because many times they wanted to use copper blocks for high heat flux, so basically CPU. Awesome. They wanted to use copper heat sinks, but copper radiator, basically it was expensive. So they were like, what if we use aluminum radiator? Everything is fine, everything is dandy, you connect it, everything works, but over time, wait a minute, there is some different color in my water, and randomly your radiator starts to leak because aluminum corroded. And what the hell happened? Inherently you created a battery, so that's why you have to, that's what we call galvanic corrosion. I provided a video down below which you should check it out for further understanding. But because water is conductive, you can have two metals far away, even though connected with a, let's say, insulative pipe, it will still cause galvanic corrosion. So it's one of those things that you have to be very mindful of, meaning if you are making a system, everything in the chain has to be of same metal. Or if you want to mix metal for some reason, for cost reasons generally, or some other reasons, you have to be very careful about it. There are ways of mitigating that issue. It has been done, especially for large heat sinks operations, but you have to be mindful of that. Generally there will be a sacrificial metal can be used, so it's like, if this will be sacrificed, and you will keep checking it, is it sacrificed? No, okay, I'm cool. Oh, it's sacrificed, okay, now replace it. So it has to be dealt with. It's a complex issue. If you want to mix, let's say, aluminum with copper to steel and iron and all that jazz, you have to be mindful of that. And how do you control how much heat is controlled? It gives you two vectors. First vector is flow rate, meaning how many liters you are moving through the radiator. That will limit like how much heat water can carry away. Then pressure simply allows the temperature. So that's how you get the control vector. It's surprisingly well thought out, surprisingly well mature technology, as in we have been maturing this for 150 years. So what we can expect in the future? Now you have to understand, this is one of those technologies. It's not new, it's not grand, it's one of those things that everything, every day, everywhere, every when is running on this. Everything from steam engines to diesel engines to every Tom, Dick and Harry coal power plant. So everything runs on it. It's one of those things that we know about it. However, we have to be better with it, simply because we are running out of fresh water. Can we use salt water for basically cooling? Yes. But it does require insanely large amount of sacrificial metal, because it will eat through metal like there is no tomorrow. So good luck with that. It can be done, but good luck. And generally, many times we are using open loop systems. We have to slowly shut them off, because this sort of open loop system looks good, does work, is cost effective, but does cost environment a serious loss of water supply. And not to mention, over time it costs the industry itself, because again, industry may not care, oh, water dropped from, let's say, 5 meters, 5 meters is too low, let's say 10 meters to 50 meters. They don't care at the first year, but they will care once it starts to go below a point where it's like, oh, okay, water reservoir, underground water reservoir is dry. At that point you have to shut down the power plant. It has happened. So we have to be very mindful of open loop water systems. We cannot just like lol it anymore. We have to be mindful about that. So wiser use will directly lead to less wastage. Less wastage, awesome. Longer lasting resources, that's super good for us. So that's the future. We have to become just wiser about its uses. Specifically, we have to slowly, brick by brick, stay away from open loop systems. So this was my presentation on water cooling. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.